Okay, well, you know, you made a real good attempt, but I don't think it quite worked out. Okay? In the first place, you're going to have a delta rho somewhere about this. So if this is now a rho star, theta star, phi star, okay? And I'm not going to draw an arrow because, again, the picture is going to get too cluttered. Then your delta rho, well, you go from some rho a little bit less than rho star to some rho a little bit bigger than rho star, the difference being delta rho. And you can visualize that as being bounded by two spheres about the origin, because when rho is constant, if you let theta and phi just go over every possible angle, you get a whole sphere. Okay, now you can think of that, digressing a little. Theta can go from 0 to 2 pi, right? So this point down here could be anywhere in the plane, okay? And if you rho is constant, of course, then it's not just anywhere in the plane, it's on a circle in the plane, okay? But when phi changes, the size of that circle, well, I shouldn't even refer to that circle, okay? I really need drawings to do this. Doing it by hand waving doesn't work too well. But again, if rho is constant, then this point lies at distance rho from the origin, and it can lie at any theta and any phi, between 0 and pi. Another thing about phi is it just goes from 0 to pi. Okay? If you want to point over here on this side, you can still get it with a phi between 0 and pi, right? Phi doesn't wrap around, because then you'd have ambiguous results. And you can think about that. Okay? So again, the point is, you got like two spheres, and this thing is sandwiched between them within a distance delta rho. Okay? So you're going to have a delta rho due to this. Okay? Now you're going to have a delta theta. What's delta theta do? Well, that restricts the projection of this point, okay, between essentially two circles, right? So it's like you're restricting this between here and here, okay? Then you've got a delta phi. What does that do? Well, that restricts you like this, okay? In other words, if phi is a little less, then this point is rotated a little bit toward the z-axis, a little more rotated a little bit away from the z-axis. So what you have here is you have, first of all, a delta rho and a rho delta phi. No sine or cosine. Okay? And then you have this wiggle room here, which gives you another dimension. So here is your rho sine phi delta theta right here. Okay? And this then causes this to go rotate back and forth. And without enough room to draw it in here, I'm going to draw it a little bigger. So we've got a delta rho, and we've got a, I need to think about how I'm going to label this. Probably shouldn't have labeled it until I worked it out. But you have a rho delta phi here, okay, corresponding what happens if phi changes. And then you have your rho sine phi delta theta. Because this goes back and forth, okay? And you can argue that these things do make right angles as the increments approach zero, all the angles approach right angles, okay? So the volume is just one row, and then you have just phi just comes in. The only thing phi does is it gives you the wiggle down here. And then you have your delta rho. Doesn't matter in what order you do these. Now when you do a partition, the order becomes important, right? But you multiply all these together, you get a delta theta, a delta phi, and a delta rho. You get a sine phi, right? And you get a rho. That halfway makes sense? Ponder. There's still things you need to understand, like why are these right angles? Okay?
Well, they're not.
Huh?
They're not right angles.
I think they are. Certainly, this approaches a right angle with this because this is radial and this is tangential to a sphere. Okay? So certainly we have this, but then why is this a right angle with this? See, you can think about that. Okay?